When the convex function f is beta smooth, we can make a better algorithm, better convergence speed with a very nice constant step size gamma. Okay, so imagine there exists non-smooth convex function like this. So why this convex function is difficult to guarantee a nice convergence rate with a constant step size? So in this case here, this convex function is non-smooth because the slope of here and slope over here are very different. So at this point, the gradient is not continuous at all. So because of this and this and this point, we cannot say this is smooth convex function. Okay, and because of the too rapid change of the slope, so the sudden change of slope, it is very difficult to control the learning rate. For instance, if our initial point is here, because the slope is too rapid, so the gradient is very high. So with some constant learning rate like learning rate gamma equal to 1, I think the gradient will go too far from here, so it will be essentially go to some bad area or diverge. So when you start from here, you have to set gamma as very tiny value like this, so that the update does not go to some very far area, but we can update like this. Okay, but on the other hand, this area slope is relatively very small compared to this area. So when you use gamma step size with very tiny value, as we did in this area, then the update ranks becomes very tiny. So we have to wait millions or billions of update iterations until we converge to the optimal point. So when the slope rapidly changes, it is very difficult to control the learning rate or step size so that we can guarantee a very nice convergence rate with gradient descent algorithm. But when the slope is very smoothly changed, like a beta smooth convex function, we can set very nice learning rate and we can guarantee a good learning speed. I will explain from now. Right, so from the beta smooth property, so this is the definition of beta smoothness, what we already discussed in the previous video, I think. And this equation just used the definition of gradient descent, xt plus 1 is equal to xt minus gamma gradient of f xt, right? So we just replace xt minus xt plus 1 by gamma times gradient f xt. That's it. And so essentially this is equal to gamma minus gamma square beta over 2 times gradient of f xt normed square. And we can optimize this term with gamma equal to 1 over beta. So this is very nice learning rate with beta smooth convex function. So for beta smooth convex function, we can optimize the right-hand side of this inequality with gamma equal to 1 over beta. And then we have this inequality ft minus fxt plus 1 always greater than or equal to 1 over 2 beta gradient of fxt normed square. Which means every time we decrease the objective function value, at least 1 over 2 beta gradient of fx normed square value. So we can always decrease the function value and with a margin of 1 over 2 beta gradient of fx t normed square. Okay, so this is very nice property. And we already have this from the vanilla analysis. And from the previous slide, we also have the upper bound of 1/2 beta gradient of fxt normed square. So we essentially know that 1/2 beta gradient of xt normed square is upper bounded by fxt minus fxt plus 1. So by replacing this term by this with keeping this inequality, we have the summation t from 0 to capital T minus 1 fxt minus fx star, the optimal point, which is less than or equal to beta over 2 times x0 minus x star normed square, Euclidean norm square, plus f0 minus fx capital T, because this is fxt minus fxt plus 1, so everything cancelled out. Remaining term is fx0 minus fxt. Okay, now let's move these two terms, fx0 minus fxt, to the left hand side. Then we have summation from t equal to 1 to capital T fxt minus fx star less than or equal to beta over 2 x0 minus x star normed square. Okay, and we also can use very interesting property of beta smooth function and gradient descent with step size 1/beta. We always decrease the objective function with step size 1/beta, which was shown here in the previous slide. So we can basically lower bound every single term using fx capital T minus fx star. Okay, so in the end we have this fx capital T minus fx star is less than or equal to beta over 2t x0 minus x star normed square. So which means when we say this is the radius square, the function objective value with capital T number of iteration, which is less than or equal to beta over 2 capital T times r square. So the conversion speed is proportional to 1 over capital T, number of iteration. So note that in the previous case, without any assumptions on objective function, without the Lipschitz continuity, in that case the conversion speed was 1 over square root 2 capital T when we ignore the other constant terms. Here, when we have beta smooth property and when we know beta, so we can set the step size or running rate by 1/beta, set to 1/beta. Then the conversion speed, running rate becomes a convergence rate becomes 1/capital T. So 1/capital T is much better than, this is better than 1/square root of T. Okay. So the beta smooth property is very important, and with the beta smooth property we can speed up the convergence.